Hi, this is Aidan Patterson speaking on the topic of Calabi-Yau manifolds for Pure Math 965, symplectic geometry. All right. The goal of this talk is to introduce the idea of a Calabi-Yau manifold and examine some of their properties. In particular, we're interested in the existence of flat metrics as well as the metric holonomy group. And finally, we'll see some examples of Calabi-Yau manifolds and look at some pretty pictures. All right, so to begin, a Calabi-Yau manifold is a compact Kähler manifold with vanishing first Chern class. There's some competing definitions, but we'll discuss some of them later. Now, there's many ways to think about the Chern class, but in our case, we care about how the Chern class is related to the Ricci form. Given a connection on M, its curvature is obtained by composing the connection with itself. Contracting with some components of the curvature, one obtains the Ricci curvature in the way that we showed. The Ricci form is then obtained by contracting the Ricci curvature with the complex structure in the second component. You can think of the Chern class as the cohomology class of the Ricci form, which can be shown to be independent of the chosen connection, in the case where we are Kähler. And if the first Chern class vanishes, then that should imply that the Ricci form is exact, which is something we'll care about. All right, so what makes Calabi-Yau manifolds so special and worthy of study? The first use of the phrase Calabi-Yau manifold was in a paper, Vacuum Configurations for Superstrings by Candelas, Horowitz, Strominger, and Witten in 1985. In this paper, the authors modeled spacetime as a direct product of 4D Minkowski space and some compact six-dimensional manifold. They deduced that this manifold was Kähler and that it had a holonomy SU3, which for us is equivalent to the vanishing of the first Chern class. Now, the condition that the first Chern class vanishes was first considered by Calabi in 1954 during a talk at the International Congress of Mathematicians. In this talk, he presented a conjecture, which is now known as the Calabi conjecture. We'll talk about this in the next slide, but this conjecture involves solving a PDE. And so while Calabi was able to show that the solution, if it existed, was unique, he was unable to show that the solutions exist in the first place. Yau provided a proof for the Calabi conjecture in 1978 by reducing this problem down to solving an elliptic PDE of complex Mong-Ampere type. All right, so here is the Calabi conjecture. So the gist is this. One chooses a representative R tilde from the first Chern class. Then one can find a metric G tilde whose associated 2 form, omega tilde, is cohomologous to the original Kähler form, and whose Ricci form, R tilde, is whose Ricci form is R tilde. You can easily see how this would specify to Calabi-Yau manifolds. If the first Chern class vanishes, then we could choose R tilde to be 0 because that is in particular closed in exact form, and find, in theory, a Ricci flat Kähler metric. In practice, these metrics are really hard to compute, and no examples besides those in the torus are known explicitly, though there are some papers which aim to find G computationally. All right, so Yau entered this picture in 1978. The Calabi conjecture can be reduced to solving the PDE in the statement shown here. The second condition is a normalization condition. The first statement tells you how the new metric is related to the old metric based on this complex function phi, it's a real function phi. And then the third is the actual statement of the PDE. All right, Calabi showed that the solutions must be unique, but Yau proved their existence. He reduced this PDE to a complex Mong-Ampere type, and this is why we refer to these manifolds as Calabi-Yau. They both collaborated to produce a conjecture which is important for these manifolds. All right, so a very special property of Calabi-Yau manifolds is that their Riemann holonomy groups are often special unitary as opposed to unitary. So recalling the definition of a holonomy group at a point P, it's the group of all possible transformations obtained by parallel transporting vectors around closed loops at P by the Levi-Civita connection. We can define the restricted Riemann holonomy group if one only considers loops that are null homotopic, meaning they are contractible to a point. And then one can also show that the point P that we start at is completely irrelevant, and so then one talks about the holonomy group of a manifold. So if one goes looking through the vacuum configurations for superstrings, they throw around the idea that the first Chern class vanishing is the same thing as the holonomy group being SU3. This is not true in general for Calabi-Yau manifolds, but the best we can say is this. A manifold is Calabi-Yau if and only if the reduced Riemann holonomy group is contained in SUM. So what can we say about the full holonomy group? So this is the best we can do. When the complex dimension is odd, then the Riemann holonomy group is SUM. And when it's even, either the manifold is simply connected, hence all loops are null homotopic, and the Riemann holonomy group is SUM, Or the fundamental group is Z2, and there's really nothing more we can say in general. You'd have to look at a specific manifold. All right, now we're going to consider a class of examples of Calabi-Yau manifolds. All right, these are going to be called complete intersection Calabi-Yau manifolds. So since CPN is compact and Kähler, it's natural to ask if any submanifolds have the structure of a Calabi-Yau manifold. In particular, we can restrict our attention to subvarieties, which are level sets of irreducible homogeneous polynomials. Calabi-Yau manifolds of this form are called complete intersection Calabi-Yau manifolds, which we abbreviate as CICY or CICY. All right. So remarkably, these examples are fundamental in the following sense. Every Calabi-Yau manifold of complex dimension m greater than or equal to 3 is biholomorphic to a projective variety in CPN. So you can retain only the complex structure this way. And so not all Calabi-Yau manifolds can be constructed as subvarieties, but one can always find one with the same underlying complex manifold structure. So what do complex projective varieties have? So what complex projective varieties have a CICY structure? All right, so it turns out that there are relatively few restrictions on the degrees of the chosen homogeneous polynomials in these to make the associated variety CICY. So here's the theorem. If we pick k generic homogeneous irreducible polynomials in n+1 variables with degrees d1 through dk, then the corresponding variety is Calabi-Yau if and only if the dimension of CPM is greater than or equal to 3 plus k, then the sum of the degrees is n+1. And so this is restrictive enough that we actually get a finite list of examples. So in this table here, we ignore degree 1 polynomials because the varieties defined by those are diffeomorphic or maybe biholomorphic to CPM-1. So we can kind of ignore them as examples. And so if we ignore polynomials of degree 1 and we look to see which ones satisfy all of these conditions, we get a very finite list. So in CP4, we can pick a generic polynomial of degree 5, and we should obtain a surface whose Euler characteristic is -200. And we denote these by y45 as in y in CP4, polynomial degree 5. CP5, there are two possible cases, one where you take the intersection of a variety defined by a 4th degree and 2nd degree polynomial, or a 3rd and 3rd, and then so on and so on for CP6 and CP7. So a particular favorite for study is the Calabi-Yau quintics, which are the first ones that we talked about, the 0 sets of quintic polynomials in CP4. They have some pretty renderings, which make them sort of fun to look at. And so this is a 2D slice of the Calabi-Yau quintic, which is z1 to the 5, z2 to the 5, and so on is equal to 0. Now, this is kind of funny because this is the picture that I think of when I think of a Calabi-Yau manifold, but apparently this is an artistic representation of a Calabi-Yau manifold and is not necessarily like a real picture of one. It's taken from a figure in Leonard Susskind's 2003 paper Superstrings, but it's adapted for artistic use, and so it's not an actual Calabi-Yau manifold picture. Either way, it's very pretty. There's been a lot of work that's gone into rendering Calabi-Yau manifolds and their intersections in finite planes, and it produces very nice pictures, and I think we'd be remiss to not take a look at them at least. All right, thank you.